Hello there.
Welcome to part 4 of the video. We are finally at the climax of the tutorial, so just hang in there a little bit longer. In this video we will take a look at the remaining systems such as enemy count and spawning mechanics, buff selector from the part 1 tutorial setup with the affix setup, music controller, stats sheets to track player stats live, a little sprinkle of custom creation skill and the stage settlement calculation. Anyway, off we go. Now let's take a look at the enemy count variable within the stage entity that listens for remaining enemies on the field. Here is the setup within the advanced data management or structure. Here is a field by field breakdown. Remaining enemy, integer. The purpose of it is to track the number of enemies currently alive on the field. This increments by +1 when a spawner activates, and decrements by -1 when an enemy dies to determine when a room, stage is cleared. 2. Total enemy, integer. The purpose of it is to track the lifetime total of enemies generated during this specific wave or floor level. Increments by +1 every time an enemy spawns, usually used for end of stage stats, progression thresholds, or scoring. Before we continue, here's a look of the custom variable setup in the stage entity. Make sure the GetEnemyCount node graph is attached to the stage entity. Let's take a look at the details of the node graph. Whenever an object in the game world is destroyed or removed, an event node automatically triggers to initiate the death registration process. To ensure system safety, the logic first utilizes an enumerations equal filter to check if the destroyed object's classification matches the entity type _creation designated for spawned enemies. A double branch node then evaluates this condition. If the entity is confirmed to be an enemy, execution proceeds, whereas non-enemy objects like destructible barrels or props cause the script to stop. Once an enemy death is validated, the system retrieves the scoreboard tracker structure from the controller entity using a custom variable node. It then splits this structure to unpack the remaining enemy count, subtracts 1 from the total to account for the defeated foe, and finally modifies and saves the updated structure back into the system. The second phase relies on a listener node that automatically awakens whenever the scoreboard data changes, reacting instantly to the subtraction completed in the previous flow. It immediately verifies that the specific variable being altered is indeed GetEnemyCount before allowing the logic to advance. The system then splits the updated post-change structure to extract the new remaining enemy value and checks if it is exactly equal to 0. If a double branch node confirms that the enemy count has hit 0, indicating the wave or room has been completely cleared, the script broadcasts 2 game-wide event signals. These final signals simultaneously open a buff selection menu for the player to choose an upgrade and heal player if the player select the healing buff from select initial buff. Enemy spawner prefab is where it handles a spawning of enemy on top of this prefab. If it was put in a square-like formation, for example, it will spawn on all 4 cubes. Refer to example pic. Here is the advanced data management setup for enemy spawner, and the following field by field breakdown. 1. Tower level, integer. The purpose of this is to define which floor this spawner is assigned to. 2. Enemy type, integer. This is an ID or enemy index used to categorize the general archetype of enemies spawning here. 3. Order number, integer. The purpose of this is to determine the sequencing, timing, or wave number for when this spawner activates. 4. Light mobs, prefab ID list. This is an expandable list holding asset IDs for basic, low-tier enemy units. 5. Elite mobs, prefab ID list. This is an expandable list holding asset IDs for stronger, specialized enemy units. 6. Boss mobs, prefab ID list. This is an expandable list holding asset IDs for major boss units. Creators can preset the mobs using the creation prefab ID here within the custom variable. Then we have the enemy spawn node graph. Make sure this node is attached to the enemy spawner prefab. Here is a detailed breakdown of the node graph. 1. Fetching the spawner data, bottom left path, get self entity, targets the spawner object itself executing this script. Get custom variable, enemy spawn, grabs the custom configuration container attached to the spawner. Split structure, enemy spawner, unpacks the configuration object we looked at previously, breaking it down into its separate properties. Tower level, enemy type, order number, light mobs, elite mobs, and boss mobs. 2. Fetching player and floor data, top path, get all entities on the field, gathers every active object currently in the game world. Get entity list by specified type, filters that massive list down specifically to find the player, entity type _ player. Get corresponding value from list, grabs the first player entry, index 0, from the filtered list. Get custom variable, floor stats, looks into that player entity to extract their current stage, floor statistics data tracking structure. Split structure, floor stats, unpacks the player's progression data, breaking it down into individual variables like current floor, current enemy level, boss floor, etc. 3. Selecting the enemy pool, middle and right intersection, get random value from list, light mobs, takes the array of light enemy IDs from the spawner config and randomly selects one specific unit ID. Get random value from list, elite mobs, takes the array of elite enemy IDs from the spawner config and randomly selects one specific unit ID. 4. Spawning execution and branching, bottom right path, multiple branches, acts as a switch, conditional node. It uses the enemy type variable pulled directly from the spawner config as the control expression. Branch sorting, depending on whether enemy type evaluates to 1, 2, or 3, likely corresponding to light, elite, or boss archetypes. The execution line splits to route the randomly selected enemy asset into the map. When entity is created, an event node tracking the exact moment the chosen enemy unit is generated into the game world, outputting the specific entity and its unique system ID, event source GUID. 5. Spawning the enemy unit, create prefab ID, takes the randomly selected enemy ID generated in the previous step. Location, rotation, gets the exact location and orientation of the spawner to spawn the enemy right on top of it. Level override, overwrites the enemy's default level using the current enemy level extracted from the player's floor stats variable. 6. Fetching stage count data. Stage entity, references the global stage or game mode controller entity. Get custom variable, check enemy count, grabs the structure tracker keeping score of how many enemies are on the field. Split structure, entity count, unpacks the data into two trackable integers, remaining enemy and total enemy. 7. Incrementing the enemy trackers, addition and modify structure, math logic, addition, adds +1 to the current remaining enemy count and +1 to the total enemy count. Update logic, modify structure, overwrites the old entity count data container with these newly incremented values so the stage manager knows an extra enemy has entered the fight. 8. Cleanup, get self-entity and destroy entity, execution convergence, all three parallel tracks feed their final white execution line into this single endpoint. Get self-entity, targets the spawner object that just completed its job. Destroy entity, completely removes the spawner from the active game world memory to prevent duplicate spawns or resource leaks. Now we have the starting buff and buff selectors. To explain our buff selector, the way it functions is that once all enemies are cleared, a signal will be sent to activate the deck selector. A total of 3 buffs will be randomly chosen through the deck selector list. However, the selections of buff follow one strict rule. Only one variant of buff will be selected. We will be using the deck selector to create the buff list UI. Head to the UI control group library and add deck selector, UI control template. Then you can head to the panel and select to option configuration to edit details in the deck list. This is how to list should look like. To explain our starting buff selector, the way it functions is that once player has selected the difficulty of the stage, there will be a blessing fountain where player is able to interact with a tab function to choose one of the 5 starting buffs that's permanent throughout the stage. This is the setup for the starting buff selector. Let's move on to the node graphs. Buff selector ON. Make sure this node graph is attached to player template. All the list on the left are deck ID being separated through each category. For example, ID 1 and 5 are attack buffs, so we will pick a random of the variant. Then we put all the random value from list into a temporary list, created using node graph variable insert value to list node. Apply buff char, make sure this node graph is attached to player template. After UI from deck selector is completed, it will run the logic for distributing the buff according to what the player select. Put the deck selector index in the multiple branches accordingly, especially if you have multiple of them. The other is the starting buff, which will be explained later. Make sure the integer of the multiple branches is attached with increase inventory item quantity after getting the character from the player. For the item config, refer to the item you have created and rsync the equipment affix. Since we have 12, there should be 12 lines of these connected. For branch 12, it's a healing full party revive node. The composite node, get all characters from player. This node is to target all the characters the player has. especially in classic mode, as the total characters is 4. Select starting buff, difficulty. This is a composite node where player can choose buffs, but it depends on the difficulty selected, so each buff requires multiple branch for each difficulty, different values. Make sure this node graph is attached to player template. This is the format of the entire composite node. Creators can pause the video and take a look. Level feels a bit silent. No worries, this is where our music controller comes in. Let's take a look at the on-event audio controller. Make sure this node is attached to the prefab music controller. Let's break the node graph down. 1. Data initialization and splitting. Fetching the audio playlists, the graph starts on the far left by getting the current entity, get self entity, and retrieving a custom data structure variable named audio list. Splitting the audio categories, a split structure node breaks down this audio list into 2 distinct categories: battle music, top path, and quest music, bottom path. 2. Random track selection logic, parallel paths. Both the battle and quest paths use identical mathematical logic to pick a random track from their respective lists. Getting list length, a get list length node determines how many tracks are in the list. Calculating the upper limit, a subtraction node subtracts 1 from the total length, adjusting for 0 indexed arrays. Generating a random index, a get random integer node uses 0 as the lower limit and the subtraction result as the upper limit to pick a random track number. Retrieving the track, a get corresponding value from list node uses that random index to extract the specific song structure, which contains data like music index, start time, and end time. 3. Event triggers and monitoring. The middle of the graph acts as the controller, listening for specific game events to dictate which path executes. Play BGM signal, a monitor signal node tracks an event named Play BGM. Double branch, conditional check. This feeds into a double branch node checking the condition is playing. If yes, top path, it triggers a start, pause player background music node to pause, resume, and then proceeds to play a random battle track. Buff selector, entity creation, bottom path, another monitor signal tracking buff selector, and the when entity is created event feed into the lower section. This area also fetches a list of players, get list of player entities on the field, to determine who should hear the music. This path ultimately triggers a random quest, background track. 4. Background music execution, output. On the far right, the graph executes the final audio commands via set player background music nodes. Target entity dynamically targets the relevant players. Music parameters, it automatically maps the selected song's parameters, music index, start time, end time, straight into the playback configuration. Default settings, the properties are configured to a volume of 100, loop playback, no, a playback speed of 1, and enable fade in, out, yes for smooth transitions. Fallback control, the final nodes in the chain are start, pause player background music nodes with recover, yes toggled, ensuring that previous music can properly resume or pause when the state changes. This is the player stat sheets node or get char stats. This allows the player to check their character stats live. Make sure this node graph is attached to the player template. Now let's break it down slowly. 1. Targeting the character, far left, get self entity into get active character of specified player. The script identifies the main player entity and finds whichever character that player is currently controlling on field. All subsequent stat queries point to this specific active character. 2. Querying the raw stats, center left blue nodes. The code splits the character's data request into 3 distinct categories to pull every relevant stat. Get character attribute, grabs basic RPG values like level, max HP, current HP, ATK, and death. Get entity advanced attribute, fetches advanced combat metrics such as crit rate, crit DMG, healing bonus, and energy recharge. Get entity elemental attribute, pulls damage bonuses and resistance stats for every specific element in the game's system. 3. The multiplier math block, center columns. You will notice a massive wall of multiplication nodes in the middle of the screen. Many game engines store stats like critical rates or elemental damage boosts as decimals, e.g., a 15.5% pyro damage boost is stored internally as 0.155. Every single one of these math nodes takes an advanced or elemental stat and multiplies it by 100, or a similar scaling factor. 4. Packing the data, large dark blue node, assemble structure, all the individual wires from the raw stats, like HP and ATK, and the multiplied stats, like crit and elemental values, converge here. This node acts like a digital box packing operation. It takes dozens of loose floating variables and organizes them into a single, clean structural object, character stats packet, so it can be handled easily by other parts of the game without requiring 50 individual wires. 5. Execution and saving, right side. The logic on the right dictates when this data snapshot actually happens. Initialization, when entity is created, when this logic script spawns, it sets up an array via assembly list and triggers a loopable timer called getStats. The update loop, when timer is triggered, every time the getStats timer ticks, check timer name, it verifies that the timer firing is indeed getStats. Set custom variable, if the check passes, it takes the fully packed data structure from the assemble structure node and saves it directly into a custom variable named getActStats. Here is another node that is part of this system. In the onEventTrigger UI, make sure this node graph is attached to player template. Let's quickly go into the explanation. 1. Detecting the UI button press, center left. When UI control group is triggered, this event fires whenever the player interacts with a mapped UI button. Multiple branches, the game checks which specific UI control group index was pressed to route the logic down 2 separate tracks. Track A, top, button mapped to ending the game early. Track B, bottom, button mapped to toggling the UI stats sheet 2. Track A, triggering a card, deck selector, top node. If the player triggers the end game button, assembly list greater than invoke deck selector, the engine bundles a quick list of indices, 1 and 2, and pops open a deck selector UI window. This works exactly like the difficulty selector we saw earlier, prompting the player to be able to end the session early or continue where they are. 3. Track B, checking existing state, bottom left. If the player triggers button 1, 0, 7, 3, 7, 4, 1, 8, 2, 8, they are trying to toggle their stats. Before changing anything, the game needs to know if the stat screen is currently open or closed. Get custom variable, player stats, into split structure. It loads the player's profile data container and extracts a Boolean variable, a true, false flag, called showStats. Double branch, this node acts as an if-else statement based on the current value of showStats. If showStats is currently true, stats are visible, it takes the yes path to turn them off. Else, it takes the no path to turn them on. 4. Flipping the visibility state, far right green nodes, depending on the outcome of the double branch, the game modifies the data and alerts the UI system. If showStats was true, top root, modify structure, it updates the player's stats data structure, changing the showStats variable to no, false. Send signal, showStats, no, it broadcasts a global game engine event, signal telling the UI system, the player has turned off stats. Close the window. If showStats was false, bottom root, it does the opposite. 5. Listening for the signal and updating the screen, bottom left to bottom center. The nodes at the very bottom respond directly to the signals sent in the previous step. Monitor signal, this node constantly listens for the showStats signal broadcasted by the far right nodes. Double branch, it reads the payload value, showStats status, attached to the signal. If yes, true, it triggers set UI control group status to UI control group status _ on for the stat window, making it physically appear on the player's screen. If no, false, it hides the panel from the screen. How about making your own enemy? This is where custom creation comes in. For this, we will be creating a simple boss using a custom creation, in this case a ruin guard. However, it does take quite a bit of setup. After that, we take a look at how the logic works. Here's the creation status node graph, let's break it down. 1. Finding the target, top left, get target entity. Before the AI can do anything, it looks up its designated threat or focus, likely the player character or the nearest enemy, and passes that entity data forward into the movement logic. 2. Managing the order of operations, middle left, execute only by sequence. This red node acts as the brain's traffic controller. It processes actions strictly in numerical order, 1 right arrow 2 right arrow 3. It will not fire step 2 until step 1 finishes, ensuring the AI performs a coherent combo rather than trying to walk and cast everything simultaneously. 3. Secure 1. Closing the distance, top center, tactic, move to the target entity, the sequencer fires pin 1. It takes the target information from the get target entity node. It sets specific navigation constraints. The entity must walk at a turn speed of 10 until it reaches an arrival detection range of 5 units from the target. Can skill be interrupted? No, this ensures the unit will stubbornly complete its march to the target without letting hit stun break its pathfinding state easily. 4. Secure 2. The primary attack combo and fallback, center right. Once the entity has successfully arrived within a range of 5 units, the sequencer moves to pin 2. This triggers a smart conditional sequence involving 2 execute skill nodes. Primary attempt, skill ID, 2. The AI first attempts to cast its main ability, skill 2. The failed execution, safety net. Notice the white line connecting the failed execution pin of skill 2 to the input of skill ID, 1. If skill 2 fires successfully, this track ends. If skill 2 fails, e.g., it's on cooldown, lacks resources, or the target moved out of the specific hitbox, the logic automatically jumps to the right and executes skill 1 as a fallback option so the AI doesn't stand idle. 5. Secure 3. The combo finisher, bottom center, execute skill ID, 1. Once step 2 concludes, regardless of whether it successfully cast skill 2 or fell back to skill 1, the sequencer moves to its final pin, 3. It forces the entity to cast skill 1 as a definitive combo finisher or standard follow-up attack. Then we have the creation status decision node graph. 1. What this code does. Execute only by sequence. Just like before, this red node controls the order of operations. It immediately fires its first action pin. 1. Switch to self-execution status. This node forces the current entity to abandon its current script container and completely swap to a brand new behavior graph. Status node graph configuration id 10821304437. This is the direct ID address of another logic file. When pin 1 fires, the game pauses this current script, packs up the AI's state, and loads the entire behavior sheet located inside ID 10821304437. Refer to the node graph above. 2. Why the previous combat code must exist first. This current node cannot exist or function in a vacuum. It acts as a pointer or trigger switch to launch the combat routine you just saw. In game development design, especially when handling AI state machines, characters switch states based on conditional logic, e.g., patrolling greater than spotted player greater than attacking. When a player finishes a run, whether they conquer the 30th floor or finally fall in battle, the stage settlement system takes over. This system calculates their performance metrics, displays the end screen dashboard, and securely updates their leaderboard rank. We have split this logic into 2 main parts: the overarching router that controls the UI, and the mathematical engine that calculates the score. Part 1, the master settlement router, stage settlement. When the settle stage signal fires, this main graph acts as the grand orchestrator for the wrap-up sequence. Make sure to attach this node to stage entity. Gathering the vitals, it fetches the global timer, validates the player entity, and pulls the session stats, current floor and total time taken. UI orchestration, it splits the execution path to push data into 3 distinct scoreboard UI displays, animating the player's floors ascended, time taken, and ultimately, their final score. Updating server state, once the final score composite node spits out the calculated integer, it bundles the score into an assembly list, flags the player's run as officially settled, and safely saves their new global leaderboard ranking. Part 2, the 2-part scoring engine, final score. Inside the final score composite node, we convert raw gameplay data into a final whole number score. To ensure the game is fair to both slow, methodical players and aggressive speedrunners, the graph splits the math into 2 distinct tracks before adding them together: linear progress and a time bonus. Here is the exact formula the graph calculates. 1. The top track, base progress score. This track ensures that simply surviving the tower is always highly rewarding, regardless of how long it takes. It multiplies the floors ascended by the difficulty multiplier. It multiplies that result by a flat constant of 100. The result, every floor cleared guarantees a baseline chunk of points. 2. The bottom track, the speedrun bonus. This track rewards true mastery by calculating an efficiency bonus, but includes safety clamps so slow players are never penalized. The target par, it calculates a dynamic target time per floor based on the difficulty tier, 45 * difficulty 60, total floors. The actual pace, it divides total time taken by floors ascended to find the player's true average time per floor. The difference, it subtracts the actual pace from the target par to find the seconds saved. The bonus scaling, it multiplies those saved seconds by 10 and then by the difficulty multiplier to generate the bonus pool. The safety clamp, crucially, this total is fed into a take larger value node compared against 0. If a player took longer than the target time, the math would become negative. This node safely clamps it to 0, ensuring they just get 0 bonus points instead of losing their hard-earned base score. 3. Validation and output. Finally, the graph adds the base score and the time bonus together and runs it through a round-to-integer operation, rounding down, for clean UI display. A final safety check verifies the score is greater than 0. If it is, the game declares a victory and awards the points. If something went horribly wrong and the score is 0 or less, it defaults to a failed state to prevent broken leaderboard entries. This scoring algorithm is an example of great player psychology. The top track says, "Good job for surviving, here is your guaranteed reward." The bottom track says, "If you want to be number 1 on the leaderboard, you need to play faster." By separating them, you create a game that is welcoming to beginners but leaves an incredibly high skill ceiling for the pros. And with that final node connected, we are completely done. Take a step back and look at what you have just accomplished. Over the last 4 videos, we have gone from a completely empty room to a fully functional, highly optimized, roguelike tower experience. In this final stretch alone, we brought the tower to life. We routed the enemy waves, programmed a dynamic music controller, built a live UI stats sheet, and gave our bosses custom skills to absolutely terrify the players. We also locked in a mathematically perfect final scoring system. So, when your players inevitably try to speedrun and break your leaderboards, the game knows exactly how to handle it. Building a system this massive and complex, within the constraints of the Miliastra Wonderland editor, is no small feat. It requires serious logic, math, and optimization. If you followed along and built this entire framework with me, you officially have the skills of a pro developer. Give yourself a massive pat on the back. Now, the foundation is yours. Take this dynamic tower system and make it your own. Add brand new environments, invent crazier blessings, or create a nightmare difficulty profile to truly punish your players. The sky, or in this case, Celestia, is the limit. Thank you so much for joining me on this incredible developer journey. Don't forget to save your project, and I will see you in the next one. Happy creating!